Okay. Yeah, okay. So welcome back, everyone. So yeah, so just go quickly over the last talk. So this is mostly trying to argue, and if you remember, like the opening remarks, I was trying to argue that machine learning, dynamical systems, and algorithmic information theory, it's like an interesting direction. And so here we used sparse kernel flows, point kernel normal forms, and PDE simplification to argue for that. And this talk is directly related to Marcus' talk, where we were trying to argue that kernel methods are directly to Kolmogorov complexity, and yeah, so it's along the same direction. So these are just try to go quickly because I think everyone is tired now. So these are things that I mentioned yesterday. So these are like things we're talking. 89 slides. We have 50 minutes left. So now you can. But I guess. Yeah, I don't know. So yeah, exactly. Do you want fast or slow version? I mean, I guess so we had a long day, you know. Yeah, okay. So I'll see how it goes. Yeah, okay. Yeah, but always have a lot of slides, so don't worry. Yeah. Yeah, okay. So maybe I should just try to step back a little bit, yeah, because the idea is, yeah, it's similar. The important question is how to analyze complex systems. I mean, I think everyone here is interested in this question, and yeah, and so so as I mentioned, so the algorithmic information theory is definitely one of the important approaches to analyze complexity. So it allows to characterize concepts like complexity, simplicity, randomness, and other things. I mean, I think this was the object of this entire conference, where we saw how AIT is important, especially in its relation to machine learning, which is the other approach to analyze complex systems, when the model is not known, but when the data is available. But among the current limitations of machine learning is that it's mostly a set of techniques and algorithms, and the theory is still underdeveloped, and it's not clear why the algorithms work and what is their domain of applicability. So as we saw in this symposium, I mean, the gap between machine learning and algorithmic information theory is quite small nowadays, and still, I mean, there is still a lot of work that can be done there. And yeah, the other direction is the other approach to analyze complex systems is the theory of dynamical systems. It allows to analyze complex systems when the model is not known, is known, but it offers non-trivial ways to analyze dynamical systems. But among its limitations is that it's limited to low-dimensional models and some small infinite-dimensional systems. So here the argument is that, yeah, in a way, I like to argue for this unified framework where we have machine learning, dynamical systems, and algorithmic information theory, where machine learning, I mean, it's not strong and theoretically speaking, but at least it can benefit from the strength of both the theory of dynamical systems and algorithmic information theory. And so it's like two legs that would allow machine learning to be stronger, mathematically speaking. And in a way, here I would like to argue that at the heart of it are kernel methods, which are like a unifying technique in a way, or a mathematical technique that will allow for machine learning, dynamical systems, and algorithmic information theory to interact with each other. And yeah, so this is what I mentioned yesterday: the machine learning for dynamical systems and vice versa, ML for AIT and vice versa. And yeah, so this is just the unification of dynamical system and machine learning is an important thing. So that's pointed out by Steve Smale almost 20 years ago, and this is how I end up starting this journey of machine learning and dynamical systems. Yeah, so this is AIT. This is what we wrote, but 2012. AIT and dynamical systems is what Kamal mentioned yesterday. How the interface of AIT and dynamical systems is an important direction as well as such. And AIT and machine learning is what we are dealing with today. And the idea is to look at kernel methods as a way to bridge the gap. So yeah, much like two parts paper, but actually there's a third one that is coming. So I try to prepare for the argument in the third paper in this talk, but I'll see how it goes. So yeah, so this is the part the talk. I mean that it's I'll talk about kernel methods and how sparse kernel flows, which is a method for learning chaotic dynamical systems, is a very efficient method, and how it can be reformulated using AIT techniques as a machine learning method. And then we'll talk about links between AIT and machine learning from the point of view of kernel methods. So we'll look at AIT for kernel methods and introduce Kolmogorov complexity-based kernels. And then we'll talk about also the minimum description length and how it can be used to reformulate sparse kernel flows, and how sparse kernel flows end up being the natural way to learn kernels. And then the other one is using the loss rank principle to learn kernels in kernel density estimation. And then kernel methods for AIT, where we saw that HSIC, which is the Hilbert-Schmidt independence criterion, in kernel method can be used as an approximation of an object in AIT, which is the algorithmic material information. And the third part is really about simplification in general. Which is about Kohlhoff transform, like simplifying PDEs and ODEs, and that the problem of simplification as such can be viewed from the point of view of AIT as a problem of simplification, that we want to reduce the Kolmogorov complexity. Yeah, so that joint work with John Kyun is here, and this is actually going to give an entire talk about it next week at the Newton Institute. So you are welcome to attend either in person or we are using dynamical system insights to show that simplification in dynamical system theory can be viewed from the point of view of AIT. Yeah, okay, so anyway, this is what Marcus was talking about, but from the point of view of kernel methods. So what are reproducing kernel Hilbert spaces that appeared in the 30s as an answer to the question, when is it possible to embed a metric space into a Hilbert space? And then the answer is that if the metric satisfies certain conditions, it is possible to embed a metric space into a special kind of Hilbert spaces that are called reproducing kernel Hilbert spaces. And among the properties of RKHS, like many, there have been several studies, especially in the 50s by Aaron John, then Schwartz in the 60s. Then they died a little bit out, and then they were resurrected by Wahba in the 90s, and then Smail boosted them, and he gave them more solid mathematical foundations. And so what are they? So before anything else, I mean, kernels are a measure of similarity. So here we want to use the fact that kernels are a measure of similarity, and then we want to link this later on to conditional complexity, where we want to say that objects are similar if they can be compressed to each other in a way. So that's in a way the intuition behind this work of linking reproducing kernels and Kolmogorov complexity. So yeah, so what are they? I mean, they are reproducing Hilbert spaces are Hilbert spaces with two extra properties. The first one is the reproducing property, which is this one here, which basically the value of function at a point is the inner product of the function with the kernel, and that the reproducing kernel the span of the reproducing kernel is dense in H. So in a way, an RKHS is a Hilbert space with a reproducing kernel whose span is dense in H. So among the properties of reproducing kernels are unicity, symmetry, dispositive definiteness in that sense, and then using this property that we can decompose the kernel as the inner product of kx dot with ky dot in H. I mean, this is like similar to what Marcus was talking about this morning, where we are trying to write this as a distance here. So we are trying to write this metric as an inner product in general in the Hilbert space. So this decomposition here is what led to introducing what we call the canonical feature map, or also called the Aaron-Jones feature map. So phi cx in that sense is equal to kx dot. And the fact that Mercer kernels, so they are, which are kernels that are continuous positive definite kernels, the fact that these kernels are positive definite and symmetric reminds us of similar properties of Gramians. Some common kernels are the monomial kernel, Gaussian, and hyperbolic tangent. And so they play an important role in learning theory, where the objective is to find an unknown function from random samples. Usually this problem is solved, can be solved analytically by minimizing this integral functional, and then this would be the closed form. But in practice, we don't know what is the raw function, what is the probability measure, and we end up performing like a minimization problem in an RKHS. So minimize this error functional plus this regularizer, which is the like a regularization in the RKHS. So this gives the following closed form for the function. So fsx is equal to cjkxxj, which are the representative theorem, which like also can be viewed as the linear combination of the canonical feature map. So it's like linearity in phi j, and the cj's themselves, they solve a system of linear equations. So we have anyway linearization in the phis, linearity in the phis, and linearity in the c's. So that's in that case what we call like learning in that context. Now the question is how to learn the kernel. So this is what method of kernel flows is about, where and this problem of learning an unknown function from random samples is ill-posed in general, but it becomes well-posed if we work in a certain Banach space with the following norm, and then reformulate the problem of learning kernels as the following min-max problem, and which leads to the following way of learning kernels that says that a kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. So yeah, so this in a way, we can view this as the link with column of complexity, because we already see like a compression problem here, which is we are saying that a kernel is good if there is no significant loss if we reduce the number of data points. So if we compress the number of data points that we are using, we are not losing much accuracy. And so this leads to the introduction of this relative error, where we have the interpolant with capital N points, which is like V star versus capital N over 2 points. So in a way, this is like a measure of compression. And so the way it works is that if you have a kernel that is like parameterized by parameter theta, and you have a large data set, so first you start like a random sample of size n, and then like a random subsample of size n over 2, which is xb versus xc. And then to find theta, one runs gradient descent in the gradient descent of rho. So theta will be parameterized as theta k plus 1 is equal to theta k minus delta gradient of rho with respect to theta. So apply this to the problem of learning chaotic dynamical systems. So basically we have time series x1 to xn, and then our goal is to forecast xn plus 1 based on this observations x1 to xn. So we cast this problem as a problem of learning an unknown function from random samples, where the past is the x and the future is the y. So we already know the closed form expression of the interpolant, which is given by the following representative theorem. And we use different variants of kernel flows to learn the kernel from data, because when we are dealing with dynamical systems, so it's not only about like learning short-term predictions, but also to learn like long-term. So this first one is the relative error is related to short-term prediction. Then if you want to learn long-term, that this will become we are looking at Lyapunov exponents. So here we are just looking at the maximal Lyapunov exponents, but it can be other Lyapunov exponents. So we'll say the kernel is good if the estimate of the maximal Lyapunov exponent from capital N points does not change much if we use capital N over 2 points. You see, again, is compression argument. Same thing for the MMD. So here we'll say that the kernel is good if the MMD between two subsamples is not much. And then another version is if we minimize, if the reconstruction of the attractor with capital N points versus capital N over 2 points does not change much. So yes, in that sense, the way where we learn the kernels is that we start. Always the question is how do you learn the kernel? Well, anyway, what is the base kernel? So we just started with sum of elemental kernels. So here we have m elemental kernels like the Gaussian or Laplace and the Mattern, etc. And then we sparsify. So we introduce this sparsification here, so the plus lambda L1 norm of theta, which are the coefficients. And see, this term here can be changed. I mean, it's not really important, but it can be just one of the criteria that we use. It could be, as I said, a short term or a long term or statistics, etc. And then we applied this to a database of large database of chaotic dynamical systems. So we use this kernel to learn this entire database, and then with the idea of sparsification, and then it worked well. And this kernel worked well in that sense. So we, for example, if you learn this kind of systems like this 3D dimensional system, so this database, I mean, has like a lot of examples from different applications, like in chemistry or physics, etc. So here we got before learning the kernel, before the sparsification versus the regular kernel flows with the sparsification. So you see like the true is blue versus prediction in red. Same thing for this example, the true system. Same thing, like before learning the kernel versus after learning the kernel. And in general, we see that there is an improvement with a short term is SMAPE distance, and then the long term is Hausdorff distance for the attractor, and we see like a reduction in the errors. Yeah, then I mean, as I said, I mean, this was like an interesting reformulation, trying to understand what compression meant. I mean, why are we learning good kernels? And that we said that, yeah, in a way that was the starting point for trying to design AIT based kernels, and trying to bridge the gap between the two. So I think I'm going to skip this AIT introduction, so everyone knows the introduction. So here I just want to focus on the link between columnar complexity and kernel methods. I mean, it's intuitively, it seems natural because kernels are a measure of similarity. And if two objects are similar, then they can be compressed to each other in that sense. So if they are not similar, then they cannot be compressed. And so, and the reasonable definition for the similarity between two objects is how difficult it is to transform them into each other. And I mean, then it becomes clear that the best concept in AIT is the length of the shortest program that computes x from y, which is kx given y, which is the conditional columnar complexity. So so here, in a way, we say that if y is uninformative or unrelated to x, then kx given y would be essentially the same as k given x. So in a way that the kxy, which is the little kxy, which is the kernel, these objects are not similar to each other. And then if y contains a lot of information relevant to x, then kx given y will be significantly smaller. And so x and y will be similar to each other. So the kernel, as a measure of similarity, will be smaller. Yeah. And so this led to introducing this column of complexity-based kernel. In a way, like we play the same game that Marcus was talking about, which is like symmetrization and trying to also make them positive semi-definite. But yeah, but as he showed, I mean that there are a lot of problems there. I mean, you cannot show it for every parameters of the kernel, but you can always manage to get them empirically speaking. I mean, this is how they are constructed in a way, in an empirical way. So the first one is based on this symmetrized conditional column of complexity, where we introduce this conditional column of complexity based kernel. And so this kernel provides a measure of similarity between x and y, where smaller values of k sim xy corresponds to greater similarity, and larger values indicate dissimilarity. Yeah.
I was thinking, but when you add that sigma in there, sorry, delta,
Yeah.
Is that like to figure out what that value is that, or was it just you just choose the value like 0?
And it's not random. Yeah, so we need to, in a way, so it's like what Marcus was saying, that yeah, in infinite dimensions, it may be hard to prove that this is like positive semi-definite, but usually in practice, you just construct the matrix, and then you compute the lowest eigenvalue, and then you shift everything by the delta. So the delta, in a way, is constructed empirically based on the data that you have. Yeah. Yeah. So these are meant to get. Yeah, it comes from the data. It's constructed from from the eigenvalues actually of the kernel matrix. Yeah. Yeah. So exactly. So this is So because in a way you can prove. I mean, like as he showed, that they are not positive semi-definite in the infinite dimensional space, but at least in the finite dimensional case, you can always try to shift the matrix. And same thing for this one here is like another symmetrized algorithmic material information kernel, which is like another kernel inspired by algorithmic material information, which is this one here. So I think same thing for the eta. We use it also to make it positive semi-definite, but because in the absolute case, it's not positive semi-definite. Anyway, and so that kernel quantifies how much knowing y reduces the complexity of describing x. And so if y contains significant information about x, then kx given 1 will be much smaller than kx, and leading to higher material information value. And then we take the max in both directions to select the direction that provides the most information for kernel construction. So in that case, the kernel captures the strongest informational relationship between x and y, and which makes of it a similarity measure. Yeah. And then we got another one which is related to the normalized compression distance. So here, so here C in a way is the approximant, and so we get like the NCD XY is given by this kernel, and then you construct also another like the kernel based on the NCD. Yeah. Yeah. So natural question is to study the universality of this kernel, the universality of these kernels. I mean that is like still like an open work. And also, like we were talking, I mean, I think we saw like a few times in this conference about the chain rule. So here the way we approximate is kx, ky given x is by considering kx comma y minus kx approximated by kx y concatenation minus kx. And so in this case, we can use like existing approximation of the compressors. But you see, I think this is finding good conditional compression techniques for ky given x is still an open problem as far as I understand. So this probably will help like finding good approximation of the kernels. And then from here, I mean, yeah, so given this, I mean, we wanted to, as I said, to reformulate this problem of learning kernels from data. And we want to show that sparse kernel flows is consistent with AIT, and it's the natural way of learning kernels from data. So this is about the MDL principle. So I think all of you know this. So here the idea, yeah, so just to compare actually between the minimizers, between regularization in machine learning versus regularization in AIT. So MDL selects the model where the loss has to be like log loss, but the regularizer is fixed and is determined by the column of complexity, while in machine learning, the loss has to be log loss. Sorry, the loss can be anything, and then the regularizer is fixed, and it's like lambda times RF. And so some differences and commonalities between MDL and RML are as follows. So the MDL, as I said, is completely general. It makes no assumption whatsoever on the underlying model class rho. So MDL is limited to log loss, while any loss can be used in RML. And RML requires choosing a penalty R and then tuning its strength by a lambda, often by cross-validation, while in the MDL theory, it dictates the penalty term. And yes, I think yeah, all of you know this part. So here what we showed is that the problem of learning the kernel from data when we are dealing with sparse kernel flows, when we start with the smaller sum of elemental kernels. So the problem of finding the best kernel reduces to the following problem. So here, as I said, you can ignore that part. It can be replaced with anything. But the most important part is just the second part, which is the p over 2 log n that is coming from the MD regularization term. And then in that sense, sparse kernel follows as a surrogate loss to make the loss computable. And yeah, so I mentioned in that case, sparse kernel flows becomes the natural way. I mean, it follows directly from AIT arguments to learn kernels from data. So there is no need to use cross-validation to justify its efficiency, and everything follows from AIT. So in that sense, I mean, the fact that sparse kernel flows considers that a kernel is good if the number of points can be halved without loss in performance, plus reducing the number of parameters in the coefficients of the sum of the kernels, show that it is consistent with AIT. And yeah, we conjecture that the minimal number of points are the covering numbers, and that this would give the best performance. Actually, we made progress along these lines. I mean, this is like the part 3 of the paper, that Marcus announced this morning. And yeah, I wouldn't have time actually to go over all the details, but just try to give you the vision that we are proposing. Yeah, in the 3 different parts of the papers. Here I'm covering mostly part 1 and part 2, but maybe part 3, like next time we'll talk. Yeah. The other issue. Yeah. So the other issue is the problem of unsupervised learning. So here we dealt like with you see that we said we have kernel methods for AIT, AIT for kernel methods, and then we also deal like supervised versus unsupervised. Like sparse kernel flows in a way is the supervised part. I mean the unsupervised part is the problem of learning kernels in kernel density estimation. So this is like an unsupervised problem. And so we have this kernel density estimate that is given by the following approximation. And yeah, so then MDL doesn't work well. And the loss rank principle, I mean, is in a way generalizes MDL to more flexible models and arbitrary loss functions. And for a data set X and model parameters theta, LORP defines a rank by counting how many hypothetical data sets achieve a loss that is less than the one that we have in our data. And so then by taking the negative log of this rank, I mean, it gives a code length extending the MDL idea of describing the X with respect to theta. So that's so in a way, this is the procedure that we suggested like to learn parameters of kernel using AIT principles. And as I said, the idea is to join between, to bridge the gap between machine learning and AIT using kernel methods. So here we are doing it for supervised and unsupervised problems. So here the way it works is that, yeah, to learn kernels in KDE using LORP, we proceed as follows. So we choose a kernel function parameterized by theta. And then we have the kernel density estimate that is given by the traditional formula. And then our goal is to learn the parameters theta. And the way it works is that we compute the negative log likelihood of the observed data set under the KDE model. And then this loss measures how well the kernel with parameters theta describes the data set. And then the way it's computed is as follows, is that we generate a hypothetical data set X prime. And then, for example, in our experiments, we just choose it to be uniformly sampled. And then we compute the rank. So for each parameterization theta, we compute the rank of the observed data set among the hypothetical data sets. So the rank is defined as the cardinality of the following set, so the number of points of elements X prime, such that the loss of theta given X prime is less or equal than the loss of theta given X. So this rank quantifies how many hypothetical data sets achieve a loss smaller than or equal to the loss of X, which are the observed data set. And the higher rank indicates that X is more typical under theta. And then, yeah, then we want to convert this rank to a code length by taking the log. And so smaller code lengths indicate that kernels that both describe X well and smaller code length indicate kernels that both describe X well and generalize to alternative data sets X prime. And so we do also the same thing. We can also get grid search, or I mean, we did it through grid search, but it can be also done through gradient descent. Yeah. So we did it for this smaller example, but I think there is much more work that can be done here. So just trying to learn the coefficient of this kernel. And yeah, so we did the same thing, like the same procedure. And yeah, so we took the different different parameters. We had a grid search, and then we noticed, for example, for here, that KDE before learning the kernel versus KTE after learning the kernel. Another issue, for example, like for another direction for kernel methods for AIT is how HSIC, that is a measure of independence, like a Hilbert-Schmidt independence criterion, can be viewed as an approximation to algorithmic material information. I think we heard that in one of the talks. So here we argued in a way that by making like an abstraction of some kernel objects, we can show that HSIC is an approximation to AMI. I think this is consistent to a discussion we had over lunch with MMD, and that maybe there is a link that can be explored there. So HSIC captures dependencies between X and Y by embedding data into a high-dimensional feature space using kernel functions. and it's capable to of detecting both linear and nonlinear relationships, making it a good tool for measuring statistical dependence. And then here we prove that, yeah, HSIC in a way is an approximation of algorithmic material information. So yeah, in a way, like one, I mean, intuitively it seems to be natural. So both of them aim to capture dependencies between variables or objects, but from different perspectives. One is statistical, kernel based, and the other one is complexity theoretic and um, coming from AIT. So in a way, so when good kernels are chosen, HC can approximate AMI, making it a practical proxy for the algorithmic notion of dependence. Yeah. So yeah, so this is what I was mentioning. And yeah, so that's in a way, I'll probably try to close here in a way. So this would be like what we are trying to prove, like we are showing in part 3. So yeah, I mean, it's still a preprint. So I just thought about giving you the vision instead of just going over all the details. So the idea then was, so we are here. So this is what I talked about in this part here. But then the natural question is that where are these kernels coming from, the kernel complexity-based kernels? And then usually, like in kernel methods and Gaussian processes, if we have a kernel, then we automatically get like a Gaussian process and define a Gaussian Hilbert space and define a Gaussian field. So in a way, I mean, if you look at the work of Marcus, I mean, he started in a way by finding like computable surrogates for Solomon Fryer. And the idea would be to argue that this kind of complexity-based kernels are approximations of what we call Solomonov kernel. And the Solomonov kernel is coming directly from the universal mixture that Marcus introduced, where this universal mixture is used to construct an embedding to go from the space of data to a different Hilbert space. And so this will give us a feature map, which is like directly inspired by AIT. And then this will give us Solomonov kernel. And then the kernel complexity-based kernels will be like an approximation of this Solomonov kernel. But the advantage of this is that once we get on good feet, and in a way we can define a new kind of Gaussian processes, which are like the Solomonov, we call it like a Solomonov Gaussian process. We also introduced like new kind of spaces. Marcus is talking like about Kolmogorov spaces, but we can also talk about Solomonov Gaussian Hilbert spaces, which are a complexity theoretic RKHS. And you can also talk about Solomonov Gaussian fields, where in a way would be able to do combine between dynamics and complexity. So these are like in a way like theoretical frameworks for just to make sure that we have a good interaction between AIT and machine learning from kernel perspective by defining the right spaces. So trying to define good Hilbert spaces where instead of having approximations of like approximate kernels, so here we go like idealized kernels in a way, which are we call like a Solomonov kernel, which are coming directly from the Solomonov prior. Yeah. So that's, yeah, I think the other part. I mean, here, as I said, we argued that for PDEs and ODEs, we can also show the same thing, that we can always, like problem of simplification in general, if you have like a nonlinear PDE, you want to transform to a simpler PDE, or like a nonlinear ODE, you want to simplify to a non-linear, like a simpler ODE, is also consistent with AIT. And yeah, so the conclusion that we introduced the method of sparse kernel flows. We reformulated this problem of learning kernels from data, and we showed that the method of sparse kernel flows can be viewed as a problem of data compression, and that the problem of learning kernels from data using kernel flows can be viewed as a problem of choosing the shortest description where the MDL principle applies, and that the method of sparse kernel flows is the natural way to learn kernels from data that is consistent with Occam's razor. So introduce kernel complexity-based kernels, and we showed that this there's also a way of learning kernels in kernel density estimation using the loss rank principle. So this results, I mean, they show that it's not necessary to use cross validation in like statistical arguments to justify efficiency of kernel flows, and that we can work directly with code lengths and complexities. As I said, I mean, yeah, this led to the diagram I just showed, which will be part 3 of the series of papers. And we applied also the same way of thinking, not only to learning kernels, but also to dynamical systems problems, like Poincare normal forms, which is a problem of simplifying ODEs using transformations. We showed that this is also consistent with the MDL principle, and same thing for the problem of simplifying PDEs, like moving from nonlinear PDEs to linear PDEs, or in general, simpler PDEs. This is also consistent with the MDL principle. And yes, our ultimate goal is to reformulate other machine learning and dynamical systems problems from an AIT perspective, and giving them more solid foundations. Yeah. Yeah, that's all. Yeah, thank you. Yeah. Let me see.